Give me 1 second. All right. Can you guys all see the screen? All right, perfect. Get started here. First, we are going to have Shiza talking about exploring perceived stress and emotional regulation. So take it away.
Hi everyone, my name is Shiza Ali and my mentor is Lisa Kearns, and today I'll be sharing insights from my recent study on how adolescents perceive and manage stress during their transition out of high school. So adolescence is a critical period marked by physical, psychological, and social changes, and it's already a vulnerable stage. But when you add in the stress of finals, college applications, and social pressures, and saying goodbye to familiar routines, it becomes overwhelming for many. So in this study, I wanted to understand how adolescents not only experience stress, but how they cope with it, and whether quantitative tools like stress scales truly capture what they're going through. This is intended to benefit parents, educators, counselors, and policymakers seeking to improve adolescent mental health programs. So this was a mixed methods design, meaning we use qualitative and quantitative data, and it was collected separately, analyzed individually, and then integrated for insights. I gathered 10 participants aged between 18 to 19, all recently graduated from high school. 60% were female, 40% male, and it was a pretty ethnically diverse group, like 50% were from America, 20% from Australia, 20% from the South Asian subcontinent, so on and so forth. So for our measures, we use the perceived stress scale, which is a 10-question survey measuring general stress levels on a 0 to 40 scale. So if you scored between 0 to 13, you have low stress, 14 to 26, moderate stress, and 27 to 40 means you have high stress. An example question from that survey is, in the last month, how often have you felt stressed or nervous? Our second measure was semi-structured interviews. So we use questions adapted from validated instruments like the Adolescent Stress Questionnaire and Student Stress Inventory alongside our own questions. And an example of a question was, what are some strategies you use to cope with academic stress? So our results, the perceived stress scale gave us an average score of 17.2 with a median of 14.5, placing most students in the moderate stress range. So 50% of participants had moderate stress, 20% had high stress, and 30% had low stress. Now, as you can see, figure one shows a right skewed distribution, meaning that while many students felt moderate stress, a few had extremely higher scores, pulling the average upward. And even the students who scored low on the stress scale shared stories in their interviews that revealed deep emotional struggles, which tells us that the scores may not always reflect the full picture. As for the interview, it revealed three major themes, which was academic pressure, coping strategies, and transitional stress. The academic pressure was the universal one. A lot of students described the fear of failure, parental expectations, and the constant pressure to perform. A lot of participants shared like panic attacks, breakdowns, and like a lot of intense competition because of the piled on stress. However, some did say that the stress helped them get things done faster. It was a motivation to push them forward and get through their problems. Secondly was coping strategies. So a lot of students coped in a wide variety of ways. Some vented to their families, others isolated, while some practiced mental framing, which is like organizing your thoughts and finding a way to push through. So these stories reveal that even if their emotional regulation isn't perfect, adolescents are actively trying to manage their stress, which says a lot on our support systems and like internal reflection, being able to be aware of what we're feeling and find a way to get through it. Third is transitional stress, so like moving from high school to college or like a gap year or work. And a lot of people said that they felt grief in leaving behind their family, teachers, and familiar routines as they felt fear about what's next because you're stepping into adulthood without a map and you're just going through blind. So, what this all means. The perceived stress scale suggested mainly moderate stress. However, the interview showed a much deeper emotional reality, such as panic attacks, breakdowns, chronic anxiety, and even identity disruption. The difference between both of these results is due to timing mainly because the perceived stress scale asks stress in the current moment, and a lot of students are on summer holidays, so they're not experiencing much stress. However, the interview questions were directed through particular like stress moments and during the past year. And another reason is because a lot of students have just gotten used to stress. So like something that would have been seen as a high stress moment has just become normalized and they downplay their experiences. Another reason is response bias. So when they're filling out their surveys, they might not feel confident enough or safe enough to admit how overwhelmed they really are. So this just says that like quantitative tools like the perceived stress scale might miss or underestimate the emotional strain adolescents endure, which is why it's really crucial to have qualitative data as well. Um, so a final takeaway is that stress is not just like a background information for adolescents, it's a defining part of their whole life and it's always there. And because of that, we should support them through and look beyond surveys and create like emotional reflection places, build context sensitive mental health support systems to recognize both visible and invisible forms of stress. Thank you so much for listening.
Awesome. Thank you so much. Really well done. And thank you to your mentor, Lisa, for being here. All right. Next we have Aditya, who's going to talk to us about challenges with projecting battery decay.
Hello, everyone. My name is Aditya Tangela, and today I'm here to present my project titled Identifying Challenges with Projecting Battery Decay Critical for the Adoption and Sizing of Renewable Energy Generation Systems, completed with the guidance of my mentor, Maura Appleberry. This work examines how battery sizing and operational patterns influence lithium-ion battery degradation and capacity retention in solar plus storage systems. We analyzed real operational battery cycling data combined with simulated solar generation and household load profiles for an average single-family home in Boston, Massachusetts, to model capacity loss over time. And this helps us understand how operational choices like depth of discharge, DOD, charge discharge rate, known as C rate, and battery size affect battery degradation and system lifetime. At the top left of the poster, you'll see the project scope, and in Figure 1 under the introduction, a typical solar plus storage setup. Figure 2, just below it, highlights a central challenge, which is that lithium-ion batteries have a higher manufacturing carbon footprint per kilowatt hour than solar panels and a much shorter operational lifespan. This mismatch motivates our focus on sizing and usage strategies for more cost-effective sustainable systems. So for a little bit about the context of the problem, solar production typically peaks around midday because that's when solar radiation intensity is highest, while energy demand usually peaks later, usually around late afternoon or evening, and this creates a supply-demand mismatch. Batteries solve this issue by storing surplus solar output and reducing it during peak demand, which is known as peak shaving, and helping align supply and use. However, lithium-ion batteries degrade over time in both the DOD, which indicates the percentage of battery capacity used during charge and discharge, and C rate, which measures how quickly the battery is being charged and discharged relative to its capacity, strongly influence how quickly this degradation happens. Understanding these effects and battery degradation is key to designing reliable, long-lasting systems. I think you accidentally moved to a different slide, but now moving on to methods. First, I modeled Boston solar irradiation in January and July using NREL's database, see Figure 3, paired with household consumption data to capture seasonal extremes. Next, I calculated net load by subtracting solar generation from energy consumption. This can be seen in Figure 4. Using a corrected load midpoint, which is essentially a straight median line drawn in the middle of the graph, is a midpoint between the minimum and maximum energy usage. I divided each day into charge and discharge intervals, which is known as peak shifting. And for battery sizing, the largest discharge in July was 17.39 kilowatt hours, which defined the small battery as it's essentially the minimum size for the battery. And the medium and large battery sizes use the same energy step, but limited depth of discharge to 60% and 20% respectively. And so I analyzed battery degradation data from Battery Archive for two chemistries, LFP and NMC, over different DODs and C rates, with smaller DOD data measured using comparison cycles every roughly 500 cycles. And finally, I built a polynomial regression model in Python to predict long-term capacity retention based on cycle count and C rate using the empirical values that were obtained from the previous few steps, and this helps simulate multi-year degradation for each battery size and chemistry. And so now for some results and key findings. From the capacity versus cycle graphs that you can see in figures 5 and 6, batteries cycled at smaller DODs and slower C rates showed a slower degradation. For example, 40 to 60% DOD at a 0.5 C rate lasts much longer than full range DOD or the faster 3C discharge rate. Also, LFP batteries outperform NMC due to greater structural stability. Figure 8 also shows that larger battery sizes, which reduce typical DOD, significantly extend operational life, but they will, of course, incur higher environmental and financial costs. You can see that this graph at the bottom of the results section. Only LFP results are shown, but similar trends hold for NMC, with LFPs still lasting longer. And then moving on to some limitations and future work. So this study focuses on cycle aging, while calendar aging, which is capacity loss over time independent of cycling, is not modeled due to data limits. So future work can integrate calendar aging, expand modeling to more climates, and use machine learning for battery health, as well as addressing battery life cycle management. So in summary, this project links battery cycling data with real-world use to show how sizing and operational choices affect battery degradation and system lifetime. These findings support better design of resilient, sustainable solar plus storage systems. I'd like to greatly thank my mentor, Maura Appleberry, for guiding me through this whole research process, as well as the Harvard Open Bio SRI program for this opportunity. Thank you for listening, and I'm happy to take any questions over Slack.
Awesome. Thank you, Aditya. Great job. All right. And sorry about the slide technical difficulties. I'll be more careful about that. Next, we have Carmen talking to us about using creative art therapy.
Stroke, which is caused by interrupted blood flow in the brain, can result in long-term motor, cognitive, and emotional challenges, including depression and anxiety. Currently, inpatient rehabilitation overlooks emotional and social difficulties and often prioritizes restoration of function. To introduce myself, my name is Carmen, and today I'll be talking about my systematic review and how creative art therapy involving activities like painting, drawing, collage making, music, and dance promotes emotional, cognitive, and physical healing. As you can see under the methods and results section, we screened over 500 studies, including a total of 6 studies conducted across 5 different countries, including Thailand, the UK, Canada, Scotland, and Israel. In Table B, we can see how the strength of evidence varied from low to high, measured on the Pedro scale for internal validity. The interventions lasted between 8 and 20 sessions and used drawing, painting, music, and mixed media, focusing on an artistic and welcoming environment for all participants. The strongest evidence came from 2 randomized controlled trials that reported improvements in motor and functional outcomes, while 2 qualitative studies described participants' perceived improvements in hand function from repetition and movements. Feasibility, safety, and acceptability were high as completion rates range from 73% to 100%. As shown in Table C, feasibility, safety, and acceptability of creative art therapy were high. Overall, the studies found that creative art therapy is a safe and well accepted by patients, with high participation rates. In one study, a group made an animation as each person molded a clay figure to represent themselves and their current state of mind, focusing on their skills in self-expression and self-acceptance. Both quantitative and qualitative data indicated gains in motivation, confidence, self-efficacy, and quality of life. Group-based settings and public displays of participants' artwork further promoted social interaction and supported rebuilding participants' self-identity. To conclude, We believe creative art therapy appears to be a beneficial adjunct to inpatient stroke rehabilitation, as it is a low-cost, autonomy-promoting intervention. While the current body of evidence is still in its early stages, existing studies suggest that it is a feasible, safe, acceptable, and potentially effective intervention. Additional rigorous randomized controlled trials are recommended to strengthen the evidence base. Thank you so much to Harvard SRI and my mentor for this opportunity and guidance.
Awesome. Thank you, Carmen. Very well done. Next, we have Noor talking to us about from waste to wellness.
Each year, about 40% of food that could be eaten never makes it to our plates. That's billions of tons of waste. But hidden in this so-called waste are valuable bioactive compounds that could help fight inflammation, support gut health, and even reduce chronic disease risk. When we think of caffeine, we think coffee or tea, and polyphenols, maybe green tea or blueberries. But both compounds are also abundant in products that we throw away. Spent coffee grounds, tea leaves, olive pomace, citrus peels, just to name a few. The challenge is these compounds are often trapped inside rigid plant cell walls. Extracting them efficiently without damaging them requires more than traditional boiling or chemical extraction. Luckily, my literature review sits at the intersection of green chemistry, sustainable food systems, and human health. My goal was to investigate how this food waste can be transformed into high-value bioactive compounds, specifically caffeine and polyphenolic antioxidants, and how these upcycled compounds interact with and modulate the gut microbiota. Upcycling, the recovering of edible compounds from materials that otherwise would have been waste, offers an opportunity to turn food waste into a health resource. In terms of extraction, I compared 3 extraction techniques that green chemistry emphasizes as the most effective for upcycling bioactives. The first of them being ultrasound-assisted extraction, which uses ultrasonic waves to create acoustic cavitation, the forming and imploding of microbubbles that rupture plant cell walls, a phenomenon depicted by Figure 1 in my poster. This mechanical disruption accelerates the release of polyphenols or caffeine, depending on the specimen, into a solvent. Second, enzyme-assisted extraction uses cell wall degrading enzymes like cellulase and pectinase to hydrolyze polysaccharides, as depicted by Figure 2, which helps free bioactives trapped in the cell wall. And finally, microwave-assisted extraction, which relies on microwave radiation to rapidly heat plant solvent mixtures, breaking down cell walls and enhancing diffusion. A reflux condenser is often paired with this method, as depicted by Figure 3, to prevent degradation of heat-sensitive bioactives like caffeine and polyphenols. These compounds respond differently to each extraction method because of their chemistry. Caffeine's small water-soluble structure makes it easy to extract with ultrasound, while larger cell wall-bound polyphenols benefit more from microwave or enzyme-based methods. Now, based on their beyond their antioxidant and anti-inflammatory properties, both compounds in their upcycled state show gut microbiota modulation potential. What makes the upcycled state distinct from the conventional is that the upcycled sources have been shown to surpass conventional ones in bioactive compound concentration. Polyphenols often reach the colon undigested, where gut microbes biotransform them into smaller phenolic acids and urolithins. These act as microbial signaling agents, boosting beneficial short-chain fatty acid production, particularly that of butyrate, and regulating tight junction proteins, which helps maintain gut barrier integrity. A significant discovery I found in recent studies reveals that in upcycled matrices, caffeine doesn't act alone. It is often extracted alongside polyphenols, which enhances antioxidant and anti-inflammatory effects. Thus, upcycled caffeine may play a dual role, stimulating the nervous system while simultaneously influencing gut microbial composition. Spent coffee ground-derived caffeine extracts in rodent models increased lactobacillus abundance and colonic butyrate levels, although there lacks human data on this. In short, food waste is not just an environmental burden, it's an untapped bioactive resource. Future research, however, should focus on human trials to clarify how extraction techniques, compound matrices, and individual microbiomes interact to influence health outcomes. If we can take yesterday's coffee grounds and turn them into tomorrow's gut health supplement, that's not just upcycling, it's rethinking food entirely. It's taking waste and turning it into wellness. Thank you for your time.
Awesome. Thank you very much, Noor. Great work as well. Next, we've got Kelly talking to us about Vision.
Hi everyone, my name is Kelly, and today I'll be presenting Vision, a novel multimodal time series architecture for EEG forecasting. Electroencephalography, or EEG, is a test that measures and records the electrical activity in the brain. EEG forecasting specifically, which is predicting future EEG signals, has numerous real-world applications, including brain-computer interfaces, seizure prediction, and driver fatigue monitoring. However, EEG forecasting is extremely challenging due to high dependence on external stimuli, the low signal-to-noise ratio, and high dimensionality of brain signals. As a result, current deep learning and regression models perform poorly in part because they do not incorporate information from external stimuli. And to date, no prior work has integrated visual modalities to develop a multimodal EEG forecasting model. So this gap in the literature is what motivated our work, leading us to design Vision with two key objectives. The first is to design a new multimodal forecasting architecture that integrates video context via a vision transformer with an inverted token EEG transformer encoder. And second, we wanted to develop a cross-attention fusion mechanism and dynamic gating module to learn and control cross-modal contributions from video to EEG forecasting. So to summarize the overall architecture of our proposed model, Vision, which is shown in the method section in Figure 2, it takes in EEG data via the time series model and video data via the vision transformer, processes the two, then fuses them through cross-attention, and uses a gating module to control how much visual context influences EEG predictions. Vision consists of four main components. It's the video transformer encoder, EEG transformer encoder, multimodal fusion module, and the gating module. So starting on the video transformer encoder, we used the Hugging Face vision transformer as the vision model. Each input video frame was divided into 16 by 16 patches, flattened, and then projected into a 256-dimensional embedding. The vision transformer then processed these embeddings and output a set of visual tokens. And the second part of Vision is the EEG transformer. We use the iTransformer model for EEG time series encoding. Each EEG segment was reinterpreted so that each channel's waveform became a single channel of tokens. Each channel was projected into a vector, passed through the iTransformer, which is what yielded the EEG tokens. Then the third part of our model is the multimodal fusion module. In order to unite the EEG and visual modalities, we implement a multi-head latent cross-attention mechanism that projects EEG and visual features into a shared latent space. Queries, which is denoted as Q, come from EEG features, while the keys K and values V come from visual features, allowing each EEG channel to be updated with weighted visual information based on similarity to capture the multiple aspects of EEG video correlations. Now moving on to the gating module. Following the cross-attention, the gating module, it computes a scalar weight for each channel, informing EEG forecasts with relevant visual cues and suppressing any irrelevant ones. After this, we then evaluated our model on the CDV dataset. This contains synchronized EEG and video data from 20 subjects, totaling 1,400 clips. EEG was recorded from 62 channels, while subjects watched 3 to 4 second video clips, each belonging to one of 40 semantic concepts. The model predicts 320 milliseconds of EEG given 3 seconds of prior EEG and video data. Since the CDV dataset provided raw EEG, we first took some pre-processing measures to clean the data. This involved DC offset removal, applying a notch filter to remove 50 Hz power line noise, and a band pass filtering between 1 to 50 Hz, which was then followed by a per-channel z-score normalization. Then, to train the model, we used the expanding window cross-validation method. So starting with an initial training set and fixed size validation block, the model grew the training window by adding one validation block at a time, retraining, and then repeating until all the data was used. After we did this training, we compared Vision against current state-of-the-art models such as WaveNet, autoregressive regression, LSTM, WGAN, and iTransformer using the root mean squared error. What we found was that Vision achieved a 0.24 RMSE, which is outperforming all the current baselines, and it shows a 17% improvement from the current state-of-the-art time series model, iTransformer. In the future, we hope to expand this research and test our model against more datasets, enhance the EEG preprocessing measures, and incorporate other modalities. I want to quickly thank my mentor, Damon Peterson, and I'm really also happy for the Harvard SRI, and I'm really happy for them for giving me this platform to do this research. Thank you.
Awesome. Thank you very much, Kelly. Well done. Next, we have Isha talking to us about neurodevelopmental diseases.
What if I told you that some parents will never get to retire? Not because they didn't work hard enough, but because it simply isn't an option. For families raising children with developmental disabilities, financial planning isn't just about the next decade, it's about a lifetime. And our research shows just how high that cost can be. Developmental disabilities are a group of conditions resulting in impairment in physical, learning, or behavior areas. Common examples include ADHD and autism spectrum disorder. These conditions are widespread. In 2016, 52.9 million children under the age of 5 worldwide had a developmental disability. Many of these conditions also require specialized care, which can often be expensive, as shown in Figure 1. It is estimated to cost between $40,000 to $60,000 per year. In addition to these numbers, statistics show that children with a developmental disability struggle to find jobs, causing a lifetime dependency. This results in families not retiring for 2, but actually retiring for 3. Our research measures the financial differences between households with and without a child of developmental disability, and also identifies where support might make the biggest difference. So let's take a look at how this was done. As shown in Figure 2, we used the survey of income and program participation data. First, we filtered our data and formed 2 groups, households with a developmentally disabled child and households without a developmentally disabled child. Then we focused on 4 key variables for household financial well-being: net worth, total assets, debt, and healthcare expenditures. Lastly, we used analytical modeling techniques to estimate the means of our variables of interest. This was done with a 2-part generalized linear model, GLM. A GLM is a flexible type of statistical model that can handle skewed data. Our GLM consisted of a logistic regression for zeros in data and a link function. Once our analytical modeling was complete, there were several unique features, as seen in Figure 4. Families with a developmentally disabled child tended to have older parents, were less likely to have married parents, and more likely to have a disabled parent themselves. Their average monthly income was about $10,000 compared to $11,000 for families without a developmentally disabled child. As seen in Figure 3 and 5, the financial differences were stark. Net worth was nearly $95,000 lower for families with a developmentally disabled child. Total debt was about $27,000 lower, but unsecured debt, like credit card and high-interest loans, were $3,000 higher. Total assets were $120,000 lower, including a $23,000 gap in retirement accounts. We found that having a developmentally disabled child is associated with lower net worth, assets, and total debt. These results hold after controlling for demographics and income, showing that income loss is not the sole driver of these differences. The results of this study show that families with a developmentally disabled child have higher unsecured debt. A large amount of unsecured debt, like credit card debt, could indicate limited financial resiliency. In contrast, families without developmentally disabled child have high secured debt, like business loans, which may show better financial situation as these debts contribute to a higher net worth over time. There are some limitations with our study. Although we included a rich set of covariates, there may be unobserved co-founding. Also, there may be other ways which spending and savings can be affected, and that might not be fully captured with the data used. Future work may consist of analyzing the financial changes before and after birth of a child and also throughout their lifespan. Policy solutions could include better outreach programs and better insurance coverage to offset these costs. With the right support, these families can better secure for both their own future and the lifelong care of their child. Finally, I would like to acknowledge and thank Open BioSRI for the platform and thank my wonderful mentor, Robbie. Thank you.
Thank you very much, Isha. Good job to you as well. Next, we have Driti talking to us about weaving science into policy using spider webs.
Good morning, everyone. Air pollution remains one of the most pressing global and environmental and public health challenges, contributing to respiratory illnesses, cardiovascular diseases, and millions of premature deaths annually, particularly in densely populated urban areas. Traditional air quality monitoring networks, while precise, are often expensive to install and maintain and require technical expertise, often provide limited spatial coverage. This leaves many communities, especially under-resourced areas, without sufficient environmental data to inform local interventions. And biomonitoring offers a complementary solution. By using living or once living materials to assess pollution, we can often obtain valuable biological information on pollutant presence, interactions, and effects, often at a fraction of the cost of conventional monitoring. Today, I'll focus on one promising yet underutilized monitoring tool, which is spiderwebs. Spiderwebs are remarkably efficient pollutant collectors since their silk is a proteinaceous material rich in fibrin and other amino acids. These can bind to contaminants through a variety of chemical interactions. Some webs are sticky, physically trapping airborne particulates, while others carry an electrostatic charge, attracting dust and soot. The silk's molecular structure, complete with functional groups like carboxyl and sulfhydryl, can chelate metal ions or bind hydrophobic organic compounds, allowing pollutants to adhere to it through a process called adsorption. These properties make spiderwebs effective for detecting a broad range of airborne contaminants, including heavy metals, polycyclic aromatic hydrocarbons, and contaminants like microplastics, bisphenols, and phthalates. The advantages of spiderwebs are compelling due to, number one, their ubiquity. You find spiderwebs everywhere, whether it be inside, outside, in parking garages, or even in rainforests. Additionally, their cost effectiveness allows for its applicability in a number of areas, whether they be under-resourced or indoor or outdoor. And such features make spiderweb biomonitoring particularly promising in areas where conventional monitors are scarce. From a policy perspective, spiderwebs can provide actionable environmental intelligence. For one, they can contribute to health risk assessments, identifying areas where carcinogenic or toxic exposures may exceed safety thresholds. Additionally, they can aid in source attribution by revealing localized distinct pollutant profiles per district or per local region. Third, they can function as screening tools, cost-effectively identifying areas that warrant more intensive regulatory monitoring. And finally, their simplicity opens opportunities for citizen science, fostering public engagement, and democratizing access to environmental data. However, like many other solutions, there are limitations to it, and these must be addressed before spiderweb biomonitoring can be integrated into formal policy frameworks. For one, there is no standardized protocol for collection, analysis, or data normalization, making cross-study comparisons pretty difficult. Additionally, efficiency varies across spiderweb species, And finally, social perceptions such as aversions to spiders should be considered when designing community-based programs. In conclusion, spider webs offer a powerful, sustainable, and widely accessible means of tracking air pollution. They hold particular promise for enhancing environmental justice by bringing monitoring capacity to places conventional networks cannot be easily reached. But to fully realize this potential, further research is needed to standardize methods, understand techniques, and accumulate mechanisms with establishing monitoring techniques. But with these advancements, spider webs could become a valuable complement to existing air quality management strategies, providing both scientific insight and policy relevant evidence to protect public health. Thank you for listening.
Awesome. Thank you so much. Very nicely done. Next, we have Amal presenting on artificial antigen presenting cells in the context of cancer immunotherapy.
Thank you. Cancer remains one of the greatest global health challenges, with roughly 20 million new cases in 2022 and projections showing that could rise to 35 million by 2050. Traditional therapies like chemo or radiation therapy can be effective but often place significant strain on patients and healthcare systems. One of the most promising approaches is immunotherapy, which works by harnessing the patient's own immune system, particularly T cells, to target and destroy cancer cells. For cancer cells to become fully activated, they need help from antigen presenting cells, or APCs, which basically just activate T cells by presenting them certain signals through surface molecules. Natural APCs like dendritic cells work well, but they're often hard to source, variable between specific donors, and aren't always scalable. This is where artificial antigen presenting cells, AAPCs, come in. They're engineered very new systems designed to mimic a natural APC function, allowing for reproducible and large-scale T cell activation in a more cost-effective manner. There's a lack of systematic reviews on APCs in the context of cancer immunotherapy from at least the last 5 years. Simply, our goal was to systematically review the literature on APCs in cancer immunotherapy, mapping the state of the field up to mid-2025, all by using the PRISMA 2020 guidelines to minimize bias. For methods, in accordance to a popular study that put various search systems through different tests and deemed specific ones viable for systematic reviews, we searched 7 major databases and platforms and trial registers, including Scopus, PubMed, Web of Science, BASE, EBSCO, Cochrane Central, and clinicaltrials.gov from their inception to July 2025. To summarize the process, we included studies including AAPCs for T cell activation in cancer or general context, and excluded non-cancer related uses, reviews, and studies that could not be reliably translated. Though all criteria weren't listed, the criteria for the study is very clear, ensuring little bias. For results, we retrieved 4,060 records, and after screening and removing duplicates, which was a high amount indicating a comprehensive search, 734 studies were deemed eligible for the study. Now, obviously, due to these surprising results, because of the field's originally conceived myopic nature, we had to generalize and group studies a lot because of journal and time restrictions. Anyways, these studies span from 1986 to 2025, and unsurprisingly, we found no clinical trials involving AAPCs specifically for cancer. Now, for a summarized discussion, most of the literature covered just AAP platforms, or some of the literature just covered AAP platforms. With main platform types, we identified were cell-based systems, microparticles, and nanoparticles, and other 3D nanostructures. However, we found that around 80% of the studies that were about using AAPCs in things like cell proliferation, experimentation, and during the creation of innovations like hydrogel in vivo delivery systems. What's clear about AAPCs are that they're extremely versatile. They provide scalable and controllable T cell activation, enabling fine-tuning for T cells, and overcome donor variability within natural APC, as seen from natural APCs. They're already a key research tool to bridge to translational therapies, especially in adoptive cell therapy. But despite rapid innovation, still a gap in clinical adoption, particularly for cancer-specific applications. Our review was comprehensive, but we didn't include Embase, a biomedical database used because of access limits, and not all eligible studies were mentioned in full detail due to limitations. And though a high caliber of rigor was upheld, there's obviously a chance for human error somewhere within the process. So, in conclusion, APCs represent a powerful, flexible tool in cancer immunotherapy. The next steps are to optimize their design to continue to optimize the design for specific tumor types, ensure scalability and cost effectiveness, and importantly, bring them into cancer-related clinical trials. And I would like to thank SRI for hosting this cohort, and thank you for Benjamin Gibbs from the Johns Hopkins University system for providing guidance throughout the creation of this review.
Awesome. Nice job. Next, we'll have Manit presenting on advancements in point of care diagnostics for, sorry, my screen just, okay, yeah, sorry. Yeah, we have Manit presenting on advancements in point of care diagnostics.
Hey everyone, hope everyone's doing well. Today I'll be talking about point of care testing in the context of dengue diagnostics, with a particular focus on multiplexing biomarkers for more accurate, timely results. To begin, what exactly is point of care? Point of care testing refers to performing diagnostic tests right at or near the patient's location, rather than sending samples to a centralized laboratory. This approach is crucial because it allows clinicians to obtain rapid results, sometimes in minutes, and make immediate decisions about patient care. You've probably seen basic examples of point of care, like pregnancy tests, glucose monitors, or even COVID tests. But in a clinical setting, point of care testing can significantly reduce the time between sample collection and diagnosis, ultimately improving patient outcomes. Now let's connect this to dengue fever. Dengue is a global health problem with hundreds of millions of infections occurring each year, primarily in tropical and subtropical regions. The challenge with dengue is that its early symptoms, like fever, headache, and muscle pain, are often indistinguishable from other infections like Zika or the flu. This overlap makes rapid, accurate diagnosis essential for timely intervention and preventing severe outcomes like dengue hemorrhagic fever or dengue shock syndrome. And this is exactly where point of care can make a huge difference. One of the most promising directions in dengue diagnostics is multiplexing biomarkers, meaning testing for multiple indicators of infection in a single device. This allows us to capture both viral markers and host immune markers at the same time. For example, the NS1 antigen is a viral protein detectable early in infection, often before antibodies are present. IgM and IgG antibodies, on the other hand, appear later. IgM in the early immune response and IgG indicating whether later stages of infection or past exposure. Combining these with host immune markers can give us a more complete picture of disease progression. Now let's talk about the immune markers. IL-10 is an anti-inflammatory cytokine, and elevated levels are often associated with severe dengue because they may suppress the immune response. TNF alpha is a pro-inflammatory cytokine that can drive tissue damage if it becomes too high. MCP1 is a chemokine that involved in recruiting immune cells to sites of infection, and IP10 plays a role in directing immune cells, particularly during infections. By measuring all these markers together, NS1, IgM, IgG, IL-10, TNF alpha, MCP1, and IP10, we can not only detect dengue earlier, but also assess the risk of severe disease in real time. Now, what tools do we currently have for dengue diagnostics? We have lateral flow assays, or LFAs, which are those rapid strip-based tests you may have seen for COVID or pregnancy. They're quick, portable, inexpensive, but they often lack the sensitivity to detect low levels of virus or antibodies. We also have ELISAs, or enzyme-linked immunoabsorbent assays, which are more sensitive and can measure specific antigens or antibodies, but they typically require lab equipment and trained personnel, making them less suited for immediate on-site diagnosis. And finally, there are the nucleic acid amplification tests like RT-PCR, which detect the viral genome itself and offer high sensitivity and specificity. While PCR is the gold standard in many laboratories, it's costly, time-consuming, and requires sophisticated infrastructure again, limiting its use for true point of care applications. Looking ahead, the future of dengue diagnostics lies in combining the strengths of these methods with multiplex biomarker detection in a single portable device. Imagine a handheld system capable of detecting NS1, IgM, IgG, and all the key immune markers in under an hour, providing both a diagnosis and a severity risk assessment on the spot. To get there, we'll need advances in microfluidics, biosensor technology, and low-cost manufacturing, along with rigorous clinical validation. In conclusion, point-of-care testing has the potential to transform how we diagnose and manage dengue, especially in resource-limited settings where laboratory access is scarce. By integrating multiple biomarkers into a single rapid test, we can detect infection earlier, monitor disease progression, and ultimately save more lives. The challenge now is not just scientific. It's about making these solutions affordable, accessible, and scalable worldwide. Now, as I end this presentation, I would like to thank my mentors, Evan Riboli and Emmy Doucette, for their time and effort, and OpenBio for this opportunity. This experience has taught me so much about this world of research that I'll be carrying along through my career in research. So thank you, and yeah, that's all I have. So
Awesome. Thank you, Manit. You guys are all doing really, really well, just so you know. Move on. We have Inan talking to us about Droid.
On March 30th of 2020, the world had stopped spinning. COVID had officially hit. Schools closed, panic spread, and Zoom stock, well, that one soared. Like most kids, I welcomed what seemed like a harmless 2-week break. But over the following year, my aunt had caught COVID early on. She became deathly ill and was hospitalized for months. And while she luckily made a full recovery, millions of others didn't. The global death toll now stands at over 7 million. COVID-19 revealed just how unprepared our systems are to track and contain pandemics. If we want a chance at saving lives in the future, we need better and smarter tools for disease tracking now. That's precisely what my project aims to build. My name is Enon, and I am proud to introduce Droid, a novel deep learning framework that simultaneously identifies both the cell type and disease status of COVID-19 from a single cell. So, let's start with the introduction. I'd like to point you guys to the left. Now, a powerful tool to understand diseases at the subcellular level is single-cell RNA sequencing. That gives us a cell's gene expression profile. You can see that in figure 2. Now, this profile can tell us two critical things. First, what type of cell it is, and second, if that cell is infected. Now, many machine learning models, you can see in MLP on figure 1 on the left, are trained to answer these questions, but they typically only focus on one task at a time. They're either really good at cell type detection or disease detection, but never both. But these tasks are related. You can't diagnose a disease if you don't know what cell it's in. So, we asked, what if we force the model to learn both tasks together? This is called a dual head network, and it's quite uncommon. It uses a shared brain to learn fundamental patterns before splitting into two specialized heads. Our theory was that this shared learning would be more accurate on both tasks. That became the blueprint for Droid. So, let's go to methods. To test this, we used a massive dataset of over 647,000 immune cells from 126 different COVID donors. We fed their gene profiles into Droid's architecture, which you can see there in figure 3. It's quite simple with only 2 linear layers and 2 nonlinear activations. We then benchmarked Droid against 2 of the most powerful models for multitask classification, XGBoost and linear support vector machines. You can see Droid's parameters in the text below in the methods section. So, what did the results say? Well, they were remarkable. As you can see in table 1, Droid achieved the highest disease detection accuracy at 91.6%, outperforming both single task baselines. And the ROC curve in figure 4 confirms this, with an area under curve of 0.984. That means if you took one random infected cell and one random healthy cell, Droid would correctly rank the infected cell as being more likely to have COVID 98.4% of the time. That is industry level accuracy. And you can see this visually in figure 5 with the UMAP, showing Droid's classification abilities with very sparse red dots and a lot of green ones. But accuracy isn't enough. We wanted to know why it was accurate. So, using a technique called trap analysis, we asked Droid which genes were most important for detecting COVID-19. And as you can see in figure 6 and 7, Droid confirmed known COVID markers like IFI27 and IFIDM3, proving that it was biologically sound. It was correct. But more excitingly, it flagged many underappreciated genes like CLU, DDIT4, and VCAN as potential novel biomarkers for COVID-19. And as you can see in figure 8, their presence in COVID-19 is quite expressive, yet they aren't considered biomarkers. But if they were, including in a qPCR set, it could improve diagnosis and save lives. Finally, we asked if these genes were truly essential for COVID-19 diagnosis. We removed the top 30 genes via ablation and retested the model. As shown in table 2, accuracy plummeted by a marking 8 percentage points and was deemed statistically significant via a Wilcoxon-signed rank test. That proves that Droid's discoveries are necessary for diagnosis. So at the end of the day, why do you care? First, Droid proves that a smart architecture beats brute force. Droid won with only 2 layers. XGBoost had 50 trees. The SVMs had 1,000 iterations. This proves the incredible potential of shared learning. Second, Droid is an engine for discovery. Droid gave us a list of novel genes that warrant experimental validation, potentially leading to faster diagnostics. And that means more lives saved. And finally, Droid is a fully transferable framework. We can train Droid on other devastating diseases like Alzheimer's, cancer, or sepsis to uncover their genetic secrets too. Listen, the COVID-19 pandemic was a wake-up call, but with intelligent, interpretable, and adaptable tools like Droid, we have a real chance to be better prepared for the future, a future where we can track diseases faster, diagnose them sooner, and ultimately save more lives. Thank you.
Wow, really well done. Really well done by everyone so far. As you can see here, we're on to our break. So we're supposed to come back at 1:35. It's supposed to be a 5-minute break, but like Saho mentioned, we're kind of running ahead of schedule, which is a good thing. So you guys can go ahead, turn the cameras off, I'll pause the recording, do whatever you got to do for the next 15 minutes or so. And then at 1:35, I'll ask that everyone has their cameras back on because our next presenter will start right at 1:36. So thank you to everyone who's gone so far, and see you guys in about 15 minutes. And then we will have Priya kick us off talking about mitochondrial mutational signature and neurodegenerative diseases.
Hi, my name is Priya Mani, and I'm from Interlake High School in Bellevue, Washington. Today, I'll be presenting my research on mitochondrial mutational pathways in neurodegenerative diseases, specifically focusing on Alzheimer's and Parkinson's. Today, we see diseases like Alzheimer's and Parkinson's affecting millions worldwide. For decades, a central aspect in these disorders is mitochondrial dysfunction, a failure in our cells' energy production. This has been described as a common red thread connecting these devastating conditions. But this raises a critical question. If the underlying problem is the same, why are the diseases so different? Why does mitochondrial failure lead to the very specific loss of dopamine-producing neurons in Parkinson's, but also cause the widespread brain atrophy in Alzheimer's? Thus, the red thread model can't fully explain these divergent patterns. To answer this question, my review proposes a new perspective, the mitochondrial mutational pathways framework. I argue that the specific disease is rather not caused by dysfunction in general, but it's the direct result of the dominant type of genomic damage that accumulates. As we can see on figures 1 to 4 on the left, the framework is built on 3 core pathways. First is the focal somatic decay pathway, which is the accumulation of mutations and deletions inside the mitochondria of a single cell over a lifetime. Second is the diffuse nuclear invasion pathway, where mitochondrial DNA fragments actually invade the cell's nucleus, causing widespread instability known as mitochondrial DNA segments, or NUMS. And third, the inherited background pathway, where one's genetic background impacts the vulnerabilities you inherit from the time of birth. This includes both your mitochondrial DNA haplogroup, nuclear genes that actually govern your mitochondria's function, and also germline mutations that make you more or less vulnerable to the other 2 pathways. Using this framework, we can now understand these diseases with a much greater precision. On figure 5 in the middle top, we noticeably can see that Parkinson's disease has a dominant focal somatic decay pathway. We see this high burden of mitochondrial DNA deletions in a very specific population of neurons. Its collaboration with the inherited mutational pathway allows the process to be made worse by inherited vulnerabilities in the mitochondrial control genes, just like Parkin or PINK1. These genes are critical for mitophagy, the process of clearing damaged mitochondria. When they are dysfunctional, damaged mitochondria are not removed. And they can then release their mitochondrial DNA, which then cascades and triggers a C-gas sting mediated inflammatory response, and then that further drives neuroinflammation. While on figure 6 in the middle bottom, we see that in contrast, Alzheimer's is a more complex pathology. While it's also influenced by these accumulative somatic point mutations and deletions, and also the inherited background through risk variants in genes like TOM40, which is a key component of the mitochondrial protein import machinery, its distinguishing feature is actually the dominance of the diffuse nuclear invasion pathway. In 2024, the ZAO study found that a high burden of these somatic nUMS in Alzheimer's brain specifically. This process where these mitochondrial DNA fragments are able to randomly insert themselves and disrupt the nuclear genome across millions of neurons over a lifetime is a really powerful mechanism for the widespread diffuse genomic damage that characterizes the disease. We can see that this new framework actually provides a roadmap for the future of precision medicine. For diagnostics, it means that we can move towards reading a patient-specific pathway. For therapeutics, it means that we can develop treatments that edit that pathway, such as using mitotalins, which is a type of molecular scissor designed to eliminate mutated mitochondrial DNA to combat the focal somatic decay pathway, or in other words, the somatic point mutations and deletions that we see. This can be seen on the right in figure 7. Overall, this framework is able to provide us a new and more precise language for understanding neurodegeneration, moving us from a generalized approach to the future of personalized medicine. Finally, I would love to thank my mentor, Mark Holton, for his incredible guidance and the Student Research Institute for this amazing opportunity. Thank you.
Thank you, Priya. Very nicely done. Next, we'll have Aloma talking to us about a systemic review of the current state, challenges, and future applications of the Da Vinci robot surgical system.
So, minimally invasive surgical techniques like laparoscopic surgery have changed the surgical field and provided an alternative to open surgery by reducing risk of infection, pain, recovery time, and scarring in patients. In minimally invasive surgery, surgical instruments and a camera are attached to long shafts and inserted through small incisions to give the surgeon access and visuals to hard-to-reach parts of the abdomen and pelvic regions. Although there are many benefits to current minimally invasive surgery, there are many limitations as well. Laparoscopic and other minimally invasive techniques only offer a 2D visual, they have reduced range of motion, and they can be very physically taxing on the surgeon. The Da Vinci robotic surgical system is a commercially available surgical robotic system that allows doctors to perform minimally invasive surgery with more comfort, control, and precision. Through the Da Vinci surgical system, surgeons are able to utilize a 3D visual, surgical instruments with 7 degrees of freedom, and experience better ergonomics. So a general review of the components of the robot. As shown in figure 1 on the bottom right, the main components of the Da Vinci robotic surgical system are the patient cart where surgical instruments are located, a surgeon console where the surgeon views and controls the surgical instruments, and a vision cart that transmits a 3D high-resolution video from the patient cart to the surgeon console. The Da Vinci uses these components to carry out a variety of surgeries in areas like urology, gynecology, transoral, colorectal, and even cardiac and lung surgeries. Currently, the Da Vinci has many benefits. It allows access to hard-to-reach places in the body and allows surgeons to perform complex multi-quadrant surgeries without even needing to move away from the surgeon console. Studies show that compared to conventional laparoscopic surgery, Da Vinci robot-assisted surgery reduces both physical and mental stress on surgeons. So even though the Da Vinci has its benefits, there are still many challenges. The Da Vinci takes considerably longer to operate with, mainly because it requires additional setup. Also, the Da Vinci can be up to a few $1,000s more expensive than conventional laparoscopic surgery, even when both surgeries are similarly successful in terms of completion and short-term surgical outcomes. Finally, the surgeon experiences a lack of tactile feedback because they are controlling the instruments through a console, but not actually making contact with the patients. To solve this problem, researchers are currently developing force feedback technology that allows sensors attached to the tip of surgical instruments to allow surgeons to experience force and tactile sensations through the surgeon console. We also analyzed other external factors that could influence the success of the Da Vinci robot. The Da Vinci requires additional training to prepare the surgeon for using the unique console and visual display. We found that trainee learning rates and quickness when completing a task increased significantly when they used robotic surgical techniques rather than laparoscopic ones. We also found that learning techniques using virtual reality and gaze-augmented virtual reality significantly improved patient performance scores. In the future, these training techniques could be used to optimize trainee performance without actually making trainees go through surgery. Additionally, we looked at the effect of nursing techniques in different patient warming types on surgical outcomes and found that using enhanced recovery after surgery protocol, or ERAS, throughout the procedure, as well as administration of warmed IV fluids to the patient significantly decreased recovery time in patients, improved patient outcomes, and helped prevent perioperative hypothermia. So the Da Vinci robot is not the only surgical robot being developed. Currently, 4 other surgical robotic systems, including the Kong Duo, the Hugo RAS, and the Edge 1000 and Revo I, are being developed and proving to be successful compared to the Da Vinci for various surgical procedures. In conclusion, the Da Vinci surgical system is transforming the way surgeries are being done and providing significant benefits for both surgeons and patients. In the future, Da Vinci robot-assisted surgery and robot-assisted surgery in general are likely to dominate the surgical field. I'd like to thank my mentor, Julie Peeling, as well as the Harvard SRI for giving me this amazing opportunity. Thank you for listening to my presentation.
Awesome. Very cool. Thank you, Alomo. Next, we have Felicia talking to us about the intersection of socioeconomic stress and prenatal substance abuse.
Good afternoon. Today I'll be discussing how low socioeconomic status, or SES, impacts fetal development, particularly in the cases of prenatal substance use. This is an important topic because it reflects a larger issue of how structural inequalities of healthcare impact vulnerable populations. And top left corner of my poster is an abstract, which summarizes how substances like marijuana and cocaine are linked to risks such as low birth weight, shortened gestation, and altered neurodevelopment. These outcomes are often worsened by low socioeconomic stressors that limit access to quality healthcare. Unfortunately, much of the existing literature is limited, with outdated studies and underrepresented groups. The goal of this paper or poster is to identify these groups and explore the relationship to assist in creating new interventions that are effective, supportive, and stigma-free. Rather than self-blame, we need to shift our focus towards addressing systemic failures that contribute to these adverse outcomes. While cocaine is not explicitly shown in this poster, it consistently shows that strong associations with neuro and physical developmental changes. Marijuana's effects show more variability, however, the harm is still evident. In the second column, marijuana exposure has been linked to small gestational age, or SGA, with SGA being present in 18.6% of exposed infants versus 8.9% in non-users. However, other studies find no significant link, likely due to differences in dosages, frequency, or just confounding substances. Timing also matters. As shown in figure 1, fetal growth is less affected at 15 weeks in comparison to 20 weeks, indicating that timing of exposure can influence outcomes. There have also been differences in vulnerability based on sex of the fetus, with male fetuses experiencing decreased baseline cortisol after exposure and higher vulnerability towards birth weight reduction at 153.09 grams compared to 84.367 grams on average. So why does this matter? Prenatal substance use is more common in low SES populations. These communities often face higher stress, limited access to accurate and non-judgmental medical advice and may rely on anecdotal or misleading online information. Marijuana use in particular is often underestimated in its risks, partly because there's a lack of clear, consistent guidance from healthcare providers. These issues indicate that it's not simply about individual choices, but also systemic inequalities that increase the likelihood of adverse fetal outcomes. The interaction between socioeconomic stress, prenatal substance use, and fetal development is a powerful driver of health disparities starting from the earliest stages of life. But even so, few studies examine these factors together. Moving forward, we need more intersectional research that integrates social, medical, and policy perspectives. This would help clarify pathways, better reflect modern substance use patterns, and ensure that findings represent the most vulnerable populations. I would like to thank my mentor, Jessalyn Froelich, and also Open Bio for this amazing opportunity, and that concludes my presentation.
Thank you, Felicia. Nice job. Next, we have Aditi, who will talk about structural analysis of the impact of SARS-CoV-2 membrane protein phosphorylation on protein-protein interactions.
Hi everyone, my name is Aditi and this is my project. So severe acute respiratory syndrome 2, also known as SARS-CoV-2, is the virus that caused the COVID-19 pandemic, which caused over 700 million reported cases and more than 7 million patient deaths. The SARS-CoV-2 virus has four main structural proteins, spike S, nucleocapsid N, envelope E, and membrane M, that aid in its ability to cause virulence in the host. The membrane protein orchestrates viral assembly of progeny viruses. These structural proteins can be visualized in Figure 1a. Post-translational modifications, PTMs, such as phosphorylation, where a phosphate group is added to a protein, can alter a protein structure and therefore function. Since viruses respond to these PTMs, this can result in new complex protein-protein interactions, also known as PPIs, between viral-to-viral and viral-to-host proteins. Focusing specifically on the M protein, it interacts with multiple structural viral proteins, along with host proteins during viral assembly. These complex PPIs are crucial for the virus to efficiently interfere with host cellular machinery during infection. As the title of this project suggests, M protein phosphorylation can impact how it interacts with other host and viral proteins, impacting its function during viral assembly. Looking at Figure 1b, there are multiple phosphorylation sites identified on the M protein from multiple cell lines. However, the impact and effect of these phosphorylation sites on the M protein's ability to interact with these other proteins during viral assembly has not been identified. This brings me to my project's objective, to examine the impact of SARS-CoV-2 membrane protein phosphorylation on its ability to engage in protein-protein interactions during viral assembly. To explore my objective, I analyzed two data sets from affinity purification mass spectrometry, or APMS studies, and selected high-confidence M protein interactors that were common to both studies. Then, using UniProt, I retrieved the amino acid sequences of multiple proteins I found to be interacting with M. In viral proteins, these were S, N, or E. And the host proteins interacting with M were REAP5, REAP6, TARS2, AAR2, ATP6V1A, ATP1B1, ANO6, and YIF1A. I then used AlphaFold Survey to generate 3D structural predictions for pairwise interactions and compare the differences between the wild-type M protein and its phosphorylated forms at serine 213 and serine 214. I then used Chimera X to visualize these interactions between the two proteins and used HawkDoc to quantify the PPI strength. I also conducted gene ontology, or GO enrichment analysis of the M protein interactors to better understand which biological terms these proteins could be classified as. I specifically conducted the GO cellular component, or GOCC, and GO biological process, or GOBP analysis. Moving on to some of the most interesting results that I found. So Figure 2 depicts the main M protein interactors from the two APMS studies. Furthermore, Figure 2b and 2c depicts the top 5 enrichment terms from the GOCC and GOBP analysis, respectively. GOCC analysis revealed the proteins to be localized primarily at the Golgi and ER, whereas the GOBP analysis identified these proteins to be related to pathways in intracellular vesicle transport and ER homeostasis. These results show that the SARS-CoV-2 M protein interactors play a role in host metabolic pathways and intracellular transport during viral infections. Figure 3 shows protein complexes of wild-type M, which is shown in magenta, and the host protein AAR2, which is shown in green, as well as M phosphorylated as serine 213, denoted as S213, and serine 214, denoted as S214. In the wild type, AAR2 interacts with M-isoleucine 217 to glutamic acid 4 of AAR2, with multiple more interactions spanning to the end of the MC terminal tail. Serine 213 phosphorylation introduced additional interactions at asparagine 216 of the C-tail, while serine 214 phosphorylation produced more extensive C-tail interactions, including direct engagement of the phosphate group at serine 214. This suggests that phosphorylation at these sites induces conformational change in the C-terminal tail, with serine 214 phosphorylation particularly notable for forming new phosphate-mediated contacts that could potentially influence viral assembly. Figure 4 depicts the protein complexes of M in purple and ATP1B1 in green, of serine 213 phosphorylated M and serine 214 phosphorylated M and ATP1B1. Wild-type M and serine 214 phosphorylated M reveal similar interaction patterns. However, phosphorylation of M S213 site did cause structural rearrangements and new interactions to form along the C-terminal tail of M. Ultimately, this study found that phosphorylation at residues S213 and S214 alters M protein-protein interactions by inducing structural changes that can strengthen or weaken binding, often increasing interactions compared to the wild-type M. Phosphorylation, especially at S213 site, drove reprogramming of M's interactions. However, it is also important to note that phosphorylation did impact all viral and host proteins, but most of them were impacted by phosphorylation. One limitation of the study is that findings are based on structural predictions and molecular docking. Experimental validation is also necessary. Some future directions include testing assays and seeing whether phosphorylation sites mentioned in the study affect PPIs. Additionally, exploring interaction hotspots mentioned here may present as promising targets for potential therapeutics. Thank you so much for your attention and for listening to my presentation.
Awesome. Really good job. Thank you, Aditi. Next, we have Gopal talking to us about environmental drivers of juvenile to adult ratios in arapaima populations of the Amazon floodplain.
Okay, thank you so much. I'm Gopal, and my mentor was Miss Priscilla, and this is my presentation. So, the Amazon floodplains are some of the most productive freshwater ecosystems on the whole of planet and biodiverse planet ecosystems on the whole of planet Earth. And, and there are a lot of fisheries in these floodplain areas that are extremely important for both the ecosystems of the Amazon and also the communities of the Amazon too. And a lot of their productivity comes from these places called floodplain lakes. So what they are is they're just these separated lakes that are sometimes connected to main channels during yearly flood pulses, which is basically the regular flooding of the floodplain areas. And so and so they often have very interesting dynamics when as many species that live in these floodplain lakes tend to feed on the flooded areas and also migrate to other parts of the region through these floodplains. And one thing about these lakes is that they're extremely diverse in the Amazon ecosystems, and they mainly they mainly vary in their morphology, their surrounding habitats, and other environmental characteristics, which are which have already been proven to affect fish abundance. However, we still don't really understand the factors that could selectively influence the survival of juveniles or adults in these floodplain lakes. And one great species that can be used to model these interactions are the arapaima, which are an iconic fish of the Amazon rainforest. And they're best known for a unique adaptation to
Sorry, my bad. Get us back here.
yes. They're
Sorry
best known
about
for
that.
they're best known for their unique adaptation to mm, breathing through air rather than through gills, which allows them to thrive in oxygen-poor floodplain lakes and predate on other fish. So in the study, we aim to uncover the environmental factors that can influence the survival uh, of juvenile or adult populations of arapaima. Okay, so our data set included various lake attributes, such as microflat coverage, lake area, the percentage of surrounding land occupied by habitats, such as Chavez Skull, which is a frequently flooded area, low and high Varzea, which are flooded forests, and other water bodies nearby. And we also had hydrological data, which consisted of daily water levels from 1995 to present, and also account data, which separated a fish into juvenile or adult categories. And we excluded the counts that had zero observed juveniles or adults, as it was impossible to truly determine the ratio of juveniles to adults, which is what we were observing. And we merged all the data sets, and we used a mixed linear model to analyze with model selection to analyze what factors would be best influencing the populations of fish. And so our final model found that Chavez Skull, which is again the flooded areas, the driest water level of the year, and also the percentage of water bodies nearby best influence the ratio of juveniles to adults. Okay, so for conclusion, the most interesting parts of this were the implication that this percentage of surrounding water bodies could be affecting the ratio of juveniles to adults, which implies that which implies that sorry that there is some factor in connectivity, which is basically the how well the floodplain lakes connect to other rivers and lakes that could be influencing the survival of juveniles. And the other main implication for this study was that there was a lot of variation in the percentage of juveniles to adults. So usually the authorities in the area just use a 3-to-1 ratio for adults to juveniles. However, there's actually a lot of variation in this ratio that was affected by these environmental factors. So there's more work that needs to be done to verify when this ratio should be used. Okay, so I just want to thank the Open Bio SRI team, 2025 cohort, and my mentor for providing valuable support for this project. Thank you.
Great job, Gopal. Sorry about the technical difficulties, man. Thanks for bearing with me. All right, next we have Aina talking about neuroplasticity driven learning.
Hi everyone, my name is Aina Trivedi, and I'm so excited to present my research project alongside my mentor Yassine Safrai, which focuses on building a hierarchical, brain-inspired neural network designed to address one of the most persistent challenges in AI, catastrophic forgetting, while enabling context-aware, lifelong learning. Let me start with the big problem my work addresses. AI systems today are incredibly powerful, but they struggle with something the human-like brain excels at, retaining old knowledge while continuously learning new information. This is known as the stability plasticity dilemma. On the left side of my poster, in the introduction section, you'll see how I've broken it down. Stability means keeping old memories intact, while plasticity is the ability to adapt to new situations. In AI, improving one often comes at the cost of the other, leading to catastrophic forgetting or interference, where an AI model rapidly loses previously learned knowledge after being trained on new data because a new learning overwrites existing neural representations. The brain, however, solves this problem in the most efficient manner, all while running on only 20 watts of power. That's where my solution comes in. As shown in the visual abstract at the top left, I designed a hierarchical brain model that uses parallel processing systems to stimulate the brain's dual memory pathways. This process starts with a surprise classifier, which mimics how the brain detects unexpected or salient events. This is inspired by the anterior cingulate cortex and the ventral striatum role in signaling prediction errors. Next, I modulate memory with neurobiological signals processing, reflecting the brain's synaptic plasticity to strengthen important memories. The final step is creating an adaptive neural map, where memory strength is determined contextually, much like how our brain links memory with meaning. If we move on to the methods section, you'll see two main phases of training. Phase 1 is synaptic formation, where the model undergoes neuroplasticity-driven foundational learning with aggressive parameters to rapidly encode essential details. Phase 2 is memory stabilization, where these representations are then fine-tuned on ambiguous examples with reduced learning traits, focused on hippocampal consolidation in the brain. To strengthen adaptability, I incorporated diversity loss to prevent premature convergence and ensure the ensemble develops distinct cognitive lenses for processing. The flowchart here parallels the brain's dual pathway processing, specialized brain streams working in parallel, while the diagram below shows my computational implementation. The results section in the bottom center shows what this approach achieves. My model reached an accuracy of 98.6 on the ambiguous test set with a weighted F1 score of 0.987. It also achieved the highest ROC-AUC value among all tested models, 0.967, outperforming both random forest of 0.891 and logistic regression of 0.823, demonstrating higher power in distinguishing between emotion classes. Most importantly, as seen in the scatter plot, there's a strong inverse correlation between uncertainty and accuracy, as R squared equals 0.903, which is a key indicator of metacognitive ability, which is the capacity of a model to assess its own confidence. On the heat map to the left, you can see how the model's attention aligns with emotionally salient keywords, reflecting a process similar to the hippocampus and amygdala in humans. Now, if you look at the conclusion in the top right, I included one of my favorite visuals from this project, a neural map of emotion categories, linked to their associated brain regions and F1 scores. This isn't just a diagram, but instead it's proof that the model organizes its internal representation in a way that parallels human affective neuroscience, clustering emotions with similar valence or arousal, just like in our own brain. In terms of future work, my next step is to extend these principles into embodied intelligence, particularly robotics. Current robots often fail in unfamiliar environments because they rely on rigid, pre-programmed behaviors. I believe that this brain-inspired framework can allow them to adapt continuously, much like humans do, without retraining from scratch. Finally, I want to acknowledge my mentor, Yassine Tafrai, for his guidance, and the Open Bio Research Institute for providing the opportunity to carry out this project. Thank you.
Excellent work, Aina. Thank you very much. Next, we have, I believe it's Doa. Let me double check. Yes, so Doa couldn't be here. I'm gonna figure out how to get this video going.
Hi, everyone.
Can everyone hear that? Yeah, awesome. Okay. If you can't hear it at any point, just unmute and let me know, but I'll let this play.
My name is Dewa Kim, and today I'd like to share with you my systematic review that explores the biological, psychological, and social influences on susceptibility and retention in cult involvements. Cults are not just a rare phenomenon. Around 3% of global population experiences some level of cult involvement in their lifetime, and yet
We can't
Hey,
hear
Alex, we
you.
can't hear anymore. I think you muted yourself.
biopsychosocial mechanisms.
Perfect, thank you.
Environment.
My bad.
Hi,
Here,
everyone. My name is Dewa.
Sorry, I had no idea that if I mute it. Thank you for letting me know. Sorry, that was dumb.
Yeah, of course.
Here, we'll just say about here.
Most of research on cults have been focused exclusively on psychological dimensions, largely ignoring the biological and social factors that collectively shape one's experiences in a cult. That's the gap that I wanted to address in this review. So I applied Engel's biopsychosocial model to understand cult membership from a more holistic perspective. This review is meant to be the first ever approach of cult membership from a multidisciplinary lens. The aim here was to identify key biopsychosocial mechanisms involved in cultic environments, ultimately to help us better identify and support those who are vulnerable to these environments. Now, As you can see under the methodological section in Figure 1, I figured out that I could follow the Prisma guideline and screen down 4 databases. This table to the right contains the keywords that I use for my search strategy. After removing the duplicates and real relevant title, I was left with 97 papers. I reviewed the abstracts and title of all 97 based on my selection criteria, and this left me with 11 studies. And I read the full text of all 11. From there, I sorted the studies into 3 main domains: neurobiological, psychological, and group social. This is when I realized that there's a significant lack of biological data from cult members, especially compared to the other 2 domains. But then I also realized that every one of these 11 studies pointed out to social conformity as a shared underlying mechanism. So in a way, I directly linked my findings to social conformity to gather new biological aspects from the culting environments. In total, we identified 10 major biopsychosocial factors associated with cult susceptibility or retention. You can see the breakdown in Figure 2 underneath the results section. And it is important to note that cult membership is not just limited to psychological dimensions, but instead consists of a collective interplay of all these 3 domains highlighted by the common intersection of the Venn diagram above. And briefly, there was 4 neurobiological factors, including mirror neuron system, oxytocin, reinforcement learning, and synchronized arousal. All of these neurobiological factors were related to the feeling of attachment and affiliated bond between the cult members that forms group identity. There were also 3 biopsychosocial factors, including cognitive closure, psychiatric traits like schizotypy, and internal coherence of belief system. The other 3 is from group social factors, including social well-being, family relations, and social precariousness. One that really stood out was family relations, because depending on the context, it could either be a protective factor or vulnerability. That's important to note that most of these factors aren't abnormal signs of mental illness, but rather reflect the common human tendencies like desire for belonging or emotional connection. And since my time is short, I won't go into each details, but I'm always happy to answer these questions on my post in Slack. Moving on to the discussion. This review's findings suggest that both the initiation and duration of cult membership are shaped by an interplay of BPS factors that can either increase vulnerability or serve as protective barriers. This highlights the need for developing a person-centered intervention rather than relying on clinical guidelines, considering that all of these cult environments are highly contextual. There are also a few limitations worth mentioning, such as lack of biological data, conversion bias due to qualitative study, and finally, the cultural bias, which is always a problem because it may overgeneralize findings in a non-Westernized world. All of these limitations highlights the need for further research to be done in this area. Last but not the least, I want to thank Sahil and the entire Harvard Open Bio team for providing me with this opportunity. And most importantly, I couldn't have done it without my mentor, Sarah, who supported to make this review possible. Lastly, I'd like to thank you for listening to my presentation.
Awesome. Thank you, Doa, virtually. Next, we have Harshit, who will be talking about a prototype CDS alert for triple negative breast cancer.
Hi, thank you. So, what is triple negative breast cancer? Triple negative breast cancer, or TNBC, is any form of breast cancer like ductal or lobular that is ER negative, PR negative, or HER and HER2 negative. This means that they lack estrogen receptors, progesterone receptors, and the human epidermal growth factor receptor 2 protein. And all of this means that effective therapies like hormone therapy that would have normally been used to treat other types of breast cancer are ineffective. So, because of how complex it is to treat, and because of the fact that it is an aggressive subtype of breast cancer, we want to be able to guide physicians so that they are able to treat it properly, which is why we developed this prototype CDS alert. First, let's go over what is CDS. CDS is clinical decision support, and it refers to anything that helps a clinician make a medical decision. And for our purposes, we used the National Comprehensive Cancer Network's clinical practice guidelines for for our alert. We constructed the following workflow, and And let's talk about um, what the alert contained. The alert function would be a non-interruptive actionable alert, meaning that it doesn't disrupt a clinician's workflow, and there's a clear action that you can take within the alert. And the actions that we opted for was adding medication to the prescribed window. And it would prescribe three medication, which is olaparib, an immunotherapy drug that is only used for patients with the BRCA1 or 2 mutations, capecitabine, which is a PARP inhibitor, that is a general TNBC drug, and pembrolizumab, which is a chemo drug that can only be used if it was the initial therapy given. And the information that would be needed for the alert is a pathology report from their first round of therapy, which is neoadjuvant therapy, and a genetic test to see if the patient was BRCA1 or 2. Um, and we evaluated the effectiveness of it using these five rights of CDS by Osharoff et al. This includes did it present the right information? Did it go to the right person? Is it in the right format? Is it in the right channel? And is it presented at the right time? And the right information refers to is the information relevant and does it help the clinician make a decision? The right person, does it appear to the clinician or someone else? The right channel, the right format means that is it an interruptive or non-interruptive alert? Is it an actionable alert, meaning that you have a clear action? And is it an informational alert, meaning that it is a block of text that appears? The right channel refers to wherever in the EHR, an electronic health record, um, uh, wherever in the electronic health record it would be presented. In our case, it would be the prescribing window, RxV. And is it presented at the right time in the clinician's workflow? And the NCCN guidelines state what the clinician's workflow should be for triple negative breast cancer, and that follows it. And our results was the prototype that we made, and we tested the prototype in MELD, which stands for Medical Logic Design. It is a software that is used for testing CDS alerts. And some limitations that we found was that the medication list wasn't extensive enough. It didn't include pembrolizumab or olaparib. And yeah, I would like to thank the Harvard SRI staff for giving me the opportunity to present this research. And I would like to give a huge thanks to my mentor for all of her guidance, Ms. Ko. Thank you.
Awesome. Thank you very much, Rashith. Great job to you as well. Move on here. Just to make sure you guys are still seeing my screen, right? Okay.
Yes.
Thank you. Sorry, I don't know what's going on. We have Adwaita talking about the potential of CRISPR-Cas9 gene editing technology to enhance CAR T-cell therapy as a targeted treatment of leukemia.
Hello, my name is Advita, and today I'm going to be presenting my lit review on the potential of CRISPR-Cas9 technology to enhance CAR T-cell therapy as a treatment for leukemia. So leukemia is a group of blood cancers that is caused by the uncontrolled growth of abnormal white blood cells in both the bone marrow and the blood. Patients with leukemia often experience symptoms such as anemia, infections, bleeding, and so much more, which ultimately hinders their health, well-being, and quality of life. So although there are a bunch of current treatments for leukemia, they often come with a lot of challenges such as treatment resistance, disease relapse, and therapy-related toxicity. One current treatment of leukemia is CAR T-cell therapy, which is when a patient's T cells are genetically modified to express chimeric antigen receptors that recognize and destroy cancer cells. Although CAR T-cell therapy is more specific and precise than other treatments such as chemotherapy and radiation, it comes with its own set of disadvantages, such as severe health side effects, complex manufacturing, and off-target risks, or accidentally attacking healthy non-cancerous white blood cells. Now, this is where CRISPR-Cas9 comes in. CRISPR-Cas9 is a genome editing tool that originates from bacterial immune systems. And how it works is it uses guide RNA to direct an enzyme called Cas9 to a specific DNA site. And at this DNA site, it either inserts or deletes genes in order to make it express whatever the goal is. So this literature review, the purpose of it is to determine whether CRISPR can enhance CAR T cell therapy by improving its targeting, persistence, and safety in order to be a more effective treatment for leukemia. To do this, I analyzed 3 different clinical trials. So all 3 of these clinical trials used CRISPR technology to modify a set of CAR T cells in patients. And all 3 of these trials had 2 main goals. The first one was to prevent graft versus host disease, also known as GVHD, and the second was to prevent host rejection. So the first trial used CRISPR to modify universal donor CAR T cells in 6 patients. And for the results, out of all the 6 patients, 4 of them achieved complete remission by day 28. And none of them expressed symptoms of typical side effects such as toxicity, GVHD, and similar methods, except it was done in 2 pediatrics that achieved molecular remission, which lasted over 6 months. The third trial was a bit different as it attempted, since it was a preclinical trial, even through the multi-gene editings. So all 3 of these trials showed similar successes, such as a lack of GVHD and higher remission rates than non-CRISPR edited CAR T cells. But however, when we're taking a technology as relatively new as CRISPR Cas9 and incorporating it into something already complex, CAR T cell therapy, or even cancer treatment of around just a couple months, which may limit. However, nature modified, as well as providing more long-term clinical for Cas9 engineered CAR T cells, are a potential have the potential to enhance CAR T cell therapy and to increase the standards of personalized cancer immunotherapy. And for this project, I'd like to thank the Harvard SRI staff, as well as the guest speakers who provided their knowledge. And finally, I'd like to express my greatest gratitude to my mentor, Daniela Liu, who provided guidance throughout this project. Thank you.
Thank you, Edwina. Very nicely done. Move on here. We have Samuel talking to us about scalable Venn score approximation with stochastic Lanczos quadrature. Samuel, if you want to help inform me a little bit, because clearly I don't know much about this. Take it away.
Sweet. Hi, everyone. Thank you, Alex. And my name's Samuel, and I'll be presenting a rapid approximation for the Venn score. So to begin, what is the Venn score? The Venn score is a domain-agnostic diversity metric for machine learning datasets. What this means is that teams can use it to diagnose error in generative outputs and evaluate model robustness across a range of fields. This matters in tasks like molecular generation, where diversity increases the chance of finding promising candidates. The problem is speed. Computing the Venn score exactly requires a full spectral decomposition of an n-by-n kernel matrix. For large datasets, that's painfully slow. A simple analysis that could take minutes can instead take hours or even days. That slows model iteration and bottlenecks scientific exploration. Our solution is SOQVS, Stochastic Lanczos Quadrature Venn score. It combines a randomized trace estimation with Lanczos algorithm so we can estimate the Venn score without a full eigen decomposition. Algorithm 3 breaks down the basic idea. For each of a few random probe vectors, we run the Lanczos algorithm to make a much smaller tridiagonal matrix. We then apply the function x log x to that small matrix and average across probes to get our estimate. So instead of one huge, expensive diagonalization, we do many quick matrix vector operations. That's the trick that makes this method fast. And all of this translates to real results. On the Moses molecular dataset with 5,000 samples, SLQVS approximates the score around 8 times faster than the exact method, with around 10% relative error on average. Additionally, SLQVS is tunable. 2 parameters control the trade-off between speed and accuracy, M the number of long steps per probe, and h, the number of random probes. Developers can increase them to reduce error or lower them to save time. As figures 1 and 2 show, at high settings, error can be driven down below 1%, and at low settings, you can achieve over a 20 times speedup. Quick note here, in figure 2, the labels were swapped, but the data is correct and it doesn't change the result or analysis. Making Venn score computation fast and tunable means teams can run many more evaluations in the same time. In molecule design, that could mean testing dozens to hundreds more candidate sets per day. For model developers, it shortens the feedback loop. Change the model, recheck diversity, and repeat all in a single day instead of over weeks. In short, SOQVS gives you a fast, controllable way to estimate the Venn score with big speedups and a predictable error, enabling quicker experiments and better results. And last but not least, I'd like to thank my mentor, Alan Denadel, for his invaluable support and guidance throughout this project, and the Harvard Open Bio staff and coordinators for the opportunity to conduct this research. Thank you so much.
Thank you, Samuel. Very nicely done. Next, we have Apurva talking to us about angiogenesis, metabolism, transcriptional relationship, and HCC and ICCA liver cancer.
Hey everyone, my name is Apurva Gautam, and today I'll be presenting my research on the angiogenesis, metabolism, transcriptional relationship in HCC and ICCA liver cancers throughout tumor progression from single-cell RNA sequencing analysis. To begin, let's talk a little bit about liver cancer. Hepatocellular carcinoma and intrahepatic cholangiocarcinoma are the two primary types of liver cancer and are among the deadliest due to late-stage diagnosis and therapy resistance. Specifically, we know that cancer cells undergo metabolic reprogramming to fuel their rapid growth, and that they also promote angiogenesis, the formation of new blood vessels, to increase their nutrient supply. While these two processes are known to be crucial for tumor growth, the relationship between them has yet to be explored, especially as the tumor progresses. This is the gap my research aims to fill. So how did we investigate this relationship? As you can see on the bottom left in our methods section, we leveraged publicly available single-cell RNA sequencing data from HCC and ICCA tumor biopsies. This technique allowed us to analyze the gene expression of thousands of individual cells, giving us a highly detailed view of the tumor's cellular landscape. Our computational approach used machine learning to answer a central question. Can we predict the metabolic state of malignant cells just by looking at their angiogenic signaling? We developed a random forest regressor model that takes the expression of angiogenic ligand genes as input and predicts the expression of specific metabolic genes. This allowed us to establish a direct transcriptional link between these two crucial processes. We also built a classification model to categorize the overall metabolic state of these cells. So our analysis led us to several key findings. First, what are the cell types that make up the liver cancer TME? As seen in figure 1, we found a diverse cellular landscape that includes not only malignant cells, but also B cells, T cells, and tumor endothelial cells, known as TECs. We observed that the proportions of these cells shift dramatically as the tumor progresses, highlighting the dynamic nature of the TME. Next, how do the cells within the TME communicate to TECs? Our receptor ligand interaction analysis revealed that a key feature of this communication is angiogenesis. We found that in early stage tumors, communication to endothelial cells is driven by fibroblasts, but in advanced stage 4 tumors, it's primarily the malignant cells themselves that are driving the signaling. Third, what is the metabolic profile of malignant cells? We also categorized the metabolic profiles of malignant cells, finding not only high enrichment in metabolic pathways, but also distinct differences between HCC and ICCA. So as you can see in figure 3, malignant cells exhibit a highly active and complex metabolic profile, with top pathways including retinoid metabolism, metabolism of fat-soluble vitamins, and metabolism of xenobiotics. This finding is consistent with the liver's natural role in nutrient processing and detoxification, suggesting these pathways are co-opted by malignant cells to support their own survival and proliferation. These type-specific metabolic signatures could be critical for informing targeted therapies. So this brings us to the core of our research. Can angiogenic ligand expression be used to predict their metabolic state? And the answer is yes. As shown in figure 4, our random forest regressor model showed strong predictive capabilities with an R-squared value of 0.73. This means that a significant portion of the variance in a malignant cell's metabolic genes can be explained by its angiogenic signaling. We also found that specific ligands like PLG, AHSG, and KNG1 are highly expressed in early stage tumors, while others like CXCL8 and TGFB2 are more dominant in late stage tumors. So these findings suggest that these ligands could be used as transcriptional biomarkers to classify the stage of the tumor. So to translate these findings into a clinically relevant application, we developed Angiometrics AI, an interface that uses our models to predict patient-specific tumor characteristics from a gene expression matrix shown in Figure 5. The tool generates a comprehensive report providing clinicians with personalized insights into the angiogenic drivers and metabolic hotspots of a patient's tumor. So this allows us to infer complex TME characteristics from a single cell population, which is a helpful approach when patient biopsy sizes are small. Future research would be to integrate spatial transcriptomics to understand the physical localization of these metabolic and angiogenic interactions. We also hope to apply our computational workflow to other cancer types and single cell populations to further unravel the cellular dynamics within the TME. Our work highlights the potential of using existing single-cell RNA sequencing data in novel ways to inform and advance personalized medicine. I'd like to thank my mentor, Sydney Caldwell, for her invaluable guidance and mentorship, as well as the Harvard OpenBio SRI team for their support. Thank you so much for your time.
Awesome. Thank you, Apoorva, and thank you, Sydney, for being here as well. It's great to see you. Next, we have another video, so let me make sure to not mute myself this time.
Hi.
From Sritha. Can you guys hear this okay?
And my project is titled Music as Medicine, Investigating Neural and Behavioral Effects in Depression. Depression and chronic stress are rising globally, and many current treatments come with side effects or don't really work well for everyone, especially for people with treatment-resistant depression. That's where music therapy comes to play. It's non-invasive, it's accessible, and it's been shown to help, but we still don't fully understand how it works on a biological level. So, my project explores both clinical and animal studies to understand how music affects the brain and whether it can really act as a therapeutic tool for depression and stress. The goal was to go beyond just mood improvement and really get to look at the science. What music is doing to the brain, the body, and stress pathways. By examining both human and animal studies, we can start to piece together a fuller picture of how music therapy might work. In the human trials, researchers used fNIRS to measure brain activity, especially in the prefrontal cortex, which is linked to emotional regulation. They also used standard clinical tools like the Hamilton Depression Rating Scale and STAI, along with physiological markers like heart rate and cortisol. Music therapy varied from active engagement like singing or improvising to passive listening, and was often combined with standard care like medication or CBT. In animal studies, rodents were exposed to stress models like CMS and CUMS models, followed by daily music exposure. Researchers then used behavioral tests like the forced swim test and the elevated plus maze to assess depression and anxiety-like behavior. They also measured biological changes like BDNF, corticosterone, inflammatory markers, and dendritic spine density. In humans, music therapy led to increased activity in the prefrontal cortex, reduced depression and anxiety scores, and lowered stress markers like heart rate and cortisol. In surgical patients, music even outperforms sedatives in reducing preoperative anxiety. In animals, music-exposed rodents showed less behavioral despair, higher BDNF levels, and better stress hormone regulation. One pig study found improvements in heart rate variability, immune responses, and even a reduction in skin lesions, suggesting a full-body stress buffering effect. All of this points to music therapy being more than just a mood booster. It's actually influencing key brain and body systems tied to emotion, stress, and healing. Because it's low risk and accessible, music therapy could be a valuable option especially for people who typically don't benefit from traditional treatments. Going forward, more research is needed to standardize protocols and explore how different types of music and delivery methods affect outcomes. But the potential is there for music to play a key role in personalized mental health care. I want to thank my mentor, Corey Knox, a PhD student at Cornell University, for her amazing support and guidance throughout this project. I'm also incredibly grateful to the Harvard Urban Bio Student Research Institute for giving me this opportunity. Thank you so much for listening and have an amazing day.
Awesome. Thank you, Srita. Great job.
Hi.
Awesome. Next, we have Pravdas, who will talk to us about classification machine learning models and how they predict overall survival in lung adenocarcinoma patients.
Hello, I'm Prabjit Singh, and today I'll be presenting our study using classification machine learning to predict long-term survival in lung adenosarcoma. Lung adenosarcoma is the most common subtype of non-small cell lung cancer and a leading cause of cancer death. Outcomes vary widely, even with similar stage and histology, reflecting real clinical and molecular heterogeneity. Standard guidelines still lean on broad clinical categories and often miss patient-level genomic signals. Our aim was to integrate multi-omics with clinical data to predict survival beyond 800 days and highlight interpretable predictors with plausible biology. We assembled clinical, mutation, and copy number data primarily from linked omics, with supplemental public features yielding over 59,000 variables. We trained 7 classifiers, including tree ensembles and a multilayer perceptron, otherwise known as an MLP, and compared them across multiple metrics. We used SHAP for interpretation. We also estimated each patient's probability of surviving past 800 days and explored treatment simulation in silico. Figure 1 shows the pipeline: multi-omic integration, pre-processing/feature selection, model training/evaluation, then SHAP-based interpretation, keeping a clear link from predictions back to specific features. Model results are summarized numerically in Table 1 and visually in Figure 2. Extra trees emerged as the strongest single model, delivering the top discrimination and the best balance of precision and recall, with fewer misclassifications in both survival categories. Cat Boost and Light GBM were close behind, with XG Boost, Random Forest, and Gradient Boosting forming a middle tier. The MLP ranked reasonably, but classified less accurately. We also tried a ridge stacking approach, which was competitive but did not surpass extra trees, so a well-tuned single learner remained optimal in this dataset. Figure 3 examines predicted survival probabilities from extra trees by true outcome. Long survival patients are shifted to higher probabilities, short survival patients cluster lower, with only limited overlap. The few confident errors likely reflect atypical tier in biology or unmeasured covariance. This separation around the median supports clinically meaningful risk ranking, not just nominal AUC gains. Figure 4 uses SHAP to rank the top 20 drivers. 3 molecular hits dominate: RAB27A, HIST1H3G, and SH3BGR. Higher RAB27A consistently lowers the predicted probability of surviving beyond 800 days, consistent with its vesicle trafficking/exosome role. HIST1H3G implicates chromatin state, and SH3BGR points to adhesion/migration pathways. Non-coding RNAs, such as HSA-MIR374A and HSA-MIR628, also rank highly, underscoring post-transcriptional regulation. Overall, combining multi-omic signals with clinical covariance yields complementary, mechanistically plausible predictors. Figure 5 focuses on RAB27A. Higher expression correlates inversely with overall survival, with a Spearman R of -0.214 and a very statistically significant p-value of 6.93 times 10 to the -6. This independent association aligns with a negative SHAP directionality and prior reports implicating RAB GTPases in metastatic competence. While RAB27A is the clearest signal, HIST1H3G and SH3BGR also warrant follow-up as potential contributors to lung adenosarcoma prognosis. In conclusion, Integrating clinical, mutation, and copy number features with supervised learning yields accurate, interpretable predictions of long-term survival in lung adenosarcoma. Extra trees provided the strongest overall performance, and SHAP linked model behavior to concrete molecular hypotheses, RAB27A, HIST1H3G, SH3BGR, and select miRNAs. Next steps include validation in independent cohorts, expansion to radiomics, so CT or MRI scans, to capture spatial heterogeneity, and refinement of the exploratory treatment simulation component. These approaches support precision oncology by improving patient-specific risk stratification and pointing to testable biological mechanisms. Thank you to my mentor, Patrick Prohatska, for his work and helping me with the research, and thank you for the Harvard Open Bio Lab providing me with this opportunity. Thank you.
Awesome. Thank you, Pravjas. Very nice job. I think that should be everyone. If there's anyone here who has not presented, please speak now. Awesome. Okay. I'm going to go ahead and pause this recording. Don't leave just yet. Give me 1 second.